Hello everyone, welcome to this all new video. In my last video in the series M401 or M302, I discussed about the Cartesian products of two sets and the concept of equivalent relation. But in this video, I'll be discussing about the equivalence class, and then we'll move on to fundamental theorems in equivalence relation. And the final topic that we'll see is the congruence relation. So let's see what an equivalence class is. Firstly, to understand the concept of equivalent class, let us consider rho be an equivalent relation on set A, and then for all x belongs to A, let box of x denote the set box of x equal to y belongs to A such that y rho x holds. Okay, first understand what I mean by y rho x. By y rho x, I means ordered pair y comma x belongs to rho. This is all it means by y rho x holds. Ordered pair y comma x belongs to rho. So what it says, first we consider the rho be an equivalent relation on set A. I hope you remember what equivalent relation is. If not, see my last video in the I button above. So we are doing is we are taking x which belongs to A and let box of x denote the set. We are defining box of x as a set where y belongs to A such that y rho x holds, and y rho x means y comma x, that is ordered pair y comma x belongs to rho. Rho means belongs to the equivalent relation on set A. So the set box of x is called equivalent class and is determined by x. The set box of x is called equivalent class determined by x with respect to rho. We are defining the set box of x as an equivalent class which is determined by x with respect to rho. The next thing we'll see is a theorem associated with equivalent class. Again, we are considering let rho be an equivalent relation on set A, as we have considered here that rho is an equivalent relation on set A, and then we are taking A which belongs to capital A. We are taking small a which belongs to capital A such that box of A not equals to 5. Okay, this is one of the rule. The theorem is such that we are considering that rho is an equivalence relation on set A. Then number one, for all A belongs to capital A, A is the set, box of A is 5, that is box of A cannot be null. Box of A cannot be null. The main reason is box of A would contain itself such that A comma A belongs to that row is the equivalent relation. That's the main reason box of A cannot be null. Yeah, the next point is if B belongs to box of A, then box of A equals to box of B where AB belongs to A and B belongs to A, capital A. The thing is, if B belongs to box of A, then obviously B is something represented here. So that is B comma A belongs to rho, that is the equivalent relation on set A. Therefore, if B belongs to A, obviously A box of A equal to box of B. Why is it so? The main thing is the symmetric property of a equivalent relation. Since rho is the equivalent relation that we considered, that's why if B belongs to A, by symmetric property we can say that box of A belongs to box of B, where A and B belongs to A, that is small a and small b, belongs to the capital A, that is the set of A. And the third thing is that for all P and Q belongs to capital A, belongs to the set A, either box of P equals to box of Q or box of Q intersection box of Q equals phi. It's the same thing actually. We are telling if P and Q are two elements that belongs to the set A, then the equivalence class of P is equal to the equivalent class of Q, or that their intersection, that is their intersection is null, that is any element which is present in both of them. Next, look at an example. For this example, consider a fraction in the form a by b, where small a and small b belongs to the set of all integers. Consider a fraction in the form a by b, where a and b belongs to the set z. You know what bold z means, such that b not equals to 0. Okay. Let us again consider fraction a by b and c by d that are defined to be related if, IFF means if and only if, AD equals BC. The next thing is this relation an equivalent relation? The question says whether this relation is an equivalence relation or not. So how will you show that this relation is an equivalent relation or not? Obviously, how can you show that to prove any relation to be equivalent relation, we need to prove three things, that is the reflexive property, the symmetric property, and the transitive property. For the reflexive property, we need to show that AB equals to AB. Obviously, we know that AB equals AB. In this equation, if we put AB equals AB, then we can write in the next line that A by B equals to A by B, which is a reflexive. In a similar way, if AB equals C by A by B equals C by D, in the similar way we can show that if A by B AD equals BC, then A by B equal to C by D, that is their symmetric. How they are symmetric? Since A and B belongs to the set of real number, also that is AB and CD belongs to a set of real number. Also CD and AB belongs to a set of real number. How if we reverse their position, they actually belong to a set of all real number. And the third case is the transitive property. To prove transitive property, we need to prove that A by B equals to C by D is equal to P by Q. Let P by Q be another element which belongs to the set set Z. In that way, we can show that this is a equivalence relation. If you have any doubt, if you still didn't understand how to prove it, you can check in the description below. I will put up a Google Drive link where you can find the solution. And the next thing is, we can observe some property from here. We can observe that an equivalence class of function is what one usually calls a rational number. In fact, rational number 1 by 2 can seem as equivalence class. How? For 1 by 2, for half or 1 by 2 being a equivalence class, we can write that it is a set of this kind of elements. It is obviously set of this kind of elements. How we can find it out? Remember? Then try. We are finding this out from the basic definition that we learned before. We understand that an equivalence class of function is what we call a rational number. In fact, we can give an example that 1 by 2 can seem as an equivalence class. That's what we actually try to prove here. The next thing is congruence relation. So congruence relation is basically an example of equivalence relation. This was introduced by Gauss. You all of you studying maths probably know who Gauss is, a famous mathematician or a scientist. So what is congruence relation? Again, we consider a fixed positive integer n which belongs to z. Set of all integers is z. We consider that a fixed positive integer n belongs to z. And we define a relation, this thing. In my last video, I have also told you about this thing, but didn't tell what this is. So again, till now, I will discuss what this thing is in the later part of this video. But till now, consider that this is some symbol and we are representing we are defining a relation with this symbol. So how this symbol defines a relation? It defines such that for all, this is for all, A and B belongs to the set of all integer A relation B implies, both side implies A minus B. If we find something A relation B or A this symbol B, this means it says A minus B, okay, which is divisible by n. So this thing A, the symbol, and B says A minus B divisible by n. That is, in simpler terms, we can say that A minus B is something nk. So that's what we found, that A minus B is nk for some k which also belongs to z. That is a set of integers. Okay. So that's how we define our relation here. So next, see what the congruence relation is. The equivalence relation is called congruence modulo n, and A congruence modulo B is also denoted by A congruence modulo B mod n. Okay, how denoted by A the symbol, B mod n. So how do you pronounce it? You pronounce it congruence modulo n of AB. Okay, this is how we pronounce it, that the equivalence relation, any equivalence relation, is called congruence modulo n and is denoted by this thing, A the symbol and mod n, pronounced as A congruence modulo n B. Okay. However, if A minus B, the most important part is, if A minus B is not divisible by n, in case this relation that we learned here, that we defined a relation, this thing, as divisible by n, however, if A minus B is not divisible by n, then you write A, B are not congruence modulo n, that is similar to a not equal to sign, mod n. Okay. Then an important consequence is to be observed that two integers A and B, if we consider A and B be two integers, those are congruence modulo n. Those are congruence modulo n if and only if A and B leave the same remainder when divisible by n. Okay, this is an important thing. It says that two integers A and B are congruence modulo n. That is, you say them as congruence modulo n if and only if A and B leave the same remainder when divisible by n. That is, when you divide A and B with n, both of them will leave the same remainder. Why is it so? Since A minus B is divisible by n, that is, when A and B are divided by n separately, then they will leave some remainder, and that remainder will be the same remainder. That's why their subtraction is divisible by n. That's the main reason. Okay. I hope you understand. If not, tell me that in the comment section. I will try to explain you there also. And the next thing is a definition of congruence modulo. What is this? Again, we consider n be a positive integer and a be any integer. We are considering n be a positive integer and a be any integer, positive or negative. Then the subset of all integers, is given by b belongs to z such that b congruence modulo n a is called congruence class modulo n of integer a and is denoted by box of a. What it says? We are considering a subset of z which is given by this set. What this set is? B belongs to z and B congruence modulo A mod n is called the congruence class of modulo n. So what B congruence modulo A mod n is? This thing basically is A minus B divisible by n. Yeah, we're told that this thing basically is A minus B divisible by n. So we are considering a set that is a subset of all integers such that any element b in that set can be represented as b a minus b divisible by n be any positive integer that we consider here, and this is called the congruence class of modulo n of integer a. That is the congruence class of modulo n of integer a, where they consider the congruence class of modulo n of the integer a, and we denote this by box of a. If you have any doubt understanding this definition part, I hope you don't have any, but in case you still have one, don't forget to check the description below. I will give you an example, handwritten example over there, so that you can understand better. In case you don't understand that example also, you are free to leave a comment. I will definitely reply to you so that I can make you understand the topic. Thank you for watching my video. Hope you liked it. So don't forget to give it a thumbs up and subscribe to my channel for similar educational videos. Thank you guys for watching. Hope to see you soon in my next video. Till then, this is Shagnik signing off.